Jnanam paramam dhyayam. Knowledge is supreme.
Okay, so in last few lectures you have already seen problems based on double delta potential, some problems are on harmonic oscillator, Hermite's polynomial. So we will be doing such problems based on Hermite polynomials. Few problems we did like a particle in one dimension, potential well, and some in the lecture some problems or some discussion was also had also taken place regarding a particle in 3-dimensional box. So we will start by a very simple exercise. So the first problem is very simple, and you can just to recap, we will start solving the first set which has 3 subset, and you have to find out in this problem that these sets are or these functions are linearly independent or linearly dependent. So from the first exercise, first problem, 3 functions are given to you. F of x is 4, g of x is x cube, and h of x is e raised to x. So in order to find whether the functions or the set of functions are linearly independent or linearly dependent, the condition that these functions must satisfy is a1 f of x, a2 g of x plus a3 h of x should be equal to 0, such that we have a1 equal to a2 equal to a3 equal to 0. Then we call this set as linearly independent. If a1, a2 and a3 are not equal to 0, then we have a set of functions which are linearly dependent. So if a1 is not equal to a2, is not equal to a3, is not equal to 0, I mean to say a1 is not equal to 0, a2 is not equal to 0 and a3 is not equal to 0, then these functions or these set of functions are linearly dependent. So the first example, from the first example you can easily see that if I substitute these functions, I have a1 times 4. So 4a1 plus a2 x cube plus a3 e raised to x is equal to 0. So this is 0 only if a1 is equal to a2 is equal to a3 is equal to 0. So this set of function are linearly independent. Okay. So in the second problem you will see that it is very simple. You can repeat the same exercise. Okay. So in part 2 or it is B, in 1b we have f of x as x, g of x as x square and h of x is x cube. Okay. So this set is linearly dependent or independent, that we have to evaluate. Similarly, you will substitute a1 x1 plus a2 x2 plus a3 x3. It can be seen from here that these the set of function is linearly independent. So when a1 is equal to a2 is equal to a3 is equal to 0, this is possible only when all the terms are 0. That means that it is linearly independent. in C part again you can easily check that this is f of x, g of x is 3 minus x square, sorry, minus x minus 4x cube, and h of x is 2x plus 3x square minus 8x cube. So, this you have to check whether it is linearly independent or not. So, now here what I do is, again I will use the trick where I will rewrite this as a1 f of x, a2 g of x and a3 h of x and equate it to 0 and find the coefficient a1, a2 and a3. So, you have to find out these coefficients and check whether this set is linearly independent or linearly dependent. So, this I leave it to you all to do it. It is very simple, you just have to substitute for f1, f2, f3 and you write it in the form we wrote it before, a1 f of x plus a2 g of x plus a3 h of x. Okay. If you find some relation between f, g and h, then it is linearly dependent. Okay. So, this is a part of exercise you can try. So, now let us go to the second part of this question. Again the problems what we did in first part, they will be similar to what we have done in the first part. Here the coordinates are given. So, first problem you have a vector A as and vector B is -2, 3 and 0. So, you are from this itself you can see that vector A is -3 times vector B. So, this implies that these vectors are linearly independent, linearly dependent, because the coefficients are not individually equal to 0. Your a1 is 1 and your a2 is 3. Okay. I have to take it on the other side and I have a1 plus 3, a plus 3b is equal to 0. Now, in the B part again we can check. B part is again simple, very simple to check. Okay. This can be done 0, 1, 2 and C is 0, 0, minus 5. Okay. Now, I skip the step of writing a1a plus a2b plus a3c. I can quickly write this as 2a1. Okay. Second term would be plus 3a1 plus a2. Okay. And the third term, okay, do not forget. So, these are in Cartesian coordinates. So, x, y and z. So, I must write here x cap, this is y cap, plus the last term would be minus a1 plus 2a2 minus 5 a3 x, y and z, z cap is equal to 0. Now, you have to equate these each coefficients such that you can calculate the value of A, B and C. So, from here if this is equal to, if A1 is equal to 0, we can obtain A2 which is also equal to 0, and when you substitute for A1 and A2, this would imply that A3 is also 0. This would imply that these vectors are linearly independent. Okay. And the same exercise goes for the last part, last problem. It will be little lengthy but not difficult. So, you can just try this out. So, A in the same manner as I did 1 and 2, 1, 2 and 3. B is -4, 1 and 7. C is 0, 10, 11 and vector D is 14, 3 and 4. This you can work out and find out whether these vectors are linearly dependent or linearly independent. It is an exercise, it will take few steps, few minutes to do, not that difficult. Okay. So, now we go to the next set of problems, that is the third problem. In problem 3, okay, let me just recollect first tutorial. In that we had calculated the time dependent wave function, right. So, this time dependent wave function we had simply calculated for a particle in one dimension. Now, here again you are given a wave function which is time independent wave function, because I have psi x comma 0 which is a e raised to minus x square upon a square. Okay. So, now in this what we do is, one way to do this is you write this in terms of you can write this in terms of the momentum in momentum representation. So, in terms of momentum space, the wave function in terms of momentum space, that is psi of p comma 0. This how will you obtain? We obtain this by taking the Fourier transform psi of x comma 0 e raised to I p dot x dx. Okay. Then there will be some normalization factor also, that is, if I write this for one dimension. So, I have, so for one dimension I have square root of 2 pi h cross, and if I write this for 3 dimension, let me make it a minus I h cross. So, now if we write it in 3 dimension, we will have 2 pi h cross the whole raised to 3 by 2, and this will be p dot r. So, now we substitute for the wave function h cross and you have this as minus I p dot x h cross dx. So, now here you have just substituted for psi x comma 0, okay, and you obtain the time, you obtain the wave function in momentum space. Now, you have to evaluate this term, which is, you will have to rewrite this in the form of a complete square. So, this to this we add and subtract. So, I will write the term that we will add and subtract will be e raised to I p square a square upon h cross square. You will have a factor of 2 coming from this is this is the square term, this is a product term, and then again a square term. So, you will have this factor, and you will write this as x by a minus p IP A upon H cross. So, I will have a factor of 4. When I am squaring, 2 becomes 4. This is what I have. Okay. And then I have a dx. Okay. So, now you have to integrate this and you obtain a final result as A. This factor of A comes from the integrand and a factor of 2 and square root of 2 pi h, and the other term would get cancelled. Okay, so this is what we get for the wave function of a particle in momentum space. Okay, remember this. And then what we will do next is we will write the time dependent Schrodinger equation. Okay, we will come back to that expression. So, we will write the time dependent Schrodinger equation as I h cross 2 psi x comma t upon 2t. This is the energy operator is equal to h phi x comma t. Okay. Now, I will write the time independent Schrodinger equation in momentum space. This would look like dou psi by dou t. I have a I h cross, I have p comma t is equal to h. I can write as an operator p square upon 2m phi. If I use phi, let us use phi throughout or psi, any one notation. So, I h cross dou phi by dou t is p square upon 2m phi p comma t. Okay. So, now let us write this as solution of this equation would be phi p comma t. You can easily take this I h cross. So, I will have a h cross upstairs I, and you can obtain the expression p. You will have a p and you will have a h cross and 2m. So, it will be p square t upon 2m h cross. Okay. So, now with some constant term. So, when I do integration by parts, this I need to do integration only, no integration by parts, only the integration would give us phi of p comma t as this expression. And remember, when I take this I have a minus sign, okay, and I have a factor of I also, which I was missing. Okay. So, I have phi of p comma t as b e raised to I p square t upon 2m h cross. Okay. Now, at t is equal to 0, what do I have? I get value of p. P is p comma 0, and we have evaluated p or phi comma 0 in our previous expression. So, this is what was our psi p comma 0, which is nothing but, which I have defined here. So, this is nothing but psi p comma 0, which I have already evaluated. So, now the wave function in the momentum space, which is time dependent wave function in momentum space, will be A upon square root of 2. I am substituting for phi of p comma 0 times you have e raised to minus p square a square upon 4 h cross square e raised to minus I p square t upon 2 m h cross. Now, I have obtained the wave function in momentum space. Similarly, we will again take a Fourier transform to obtain the wave function in position space. So, psi of x comma t will be nothing but, again I am skipping one step where you have to integrate. This is what I obtain, integral. So, I will just write down and then you have to integrate phi of p comma t e raised to I p dot x upon h cross, okay. And that will give me a final expression as 2 a upon square root of 2, and when I integrate this from the whole range, the final expression which I get is, let me write it here. I will have, so here from this I will get p square a square, that is this term. I will have this term minus p square a square upon 4 h cross square and this term. So, on integrating out this term, one can finally obtain a square plus 2 I h cross t upon m. This is the expression, times you will have an additional factor of exponential minus h square upon a square plus. So, this is in the exponent itself 2 I h cross t by m. Okay. So, this is the expression for the time dependent wave function. So, first what we did was that we first write the wave function in momentum space. Once we obtain the wave function, time dependent wave function, time independent wave function in the momentum space, then what we did was we wrote the time independent Schrodinger equation in momentum space. You have to do all lot of integration wherein you complete the square and find out the definite integral, and then again we take the Fourier transform. So, we go from the momentum position space to momentum space. So, this is another way of calculating the wave function, which is time independent. From the time dependent wave independent wave function, we obtain the time dependent wave function. So, the next problem will be fourth problem involves a little bit of thinking. So, in this problem you are given a particle which is moving in one dimension in the harmonic oscillator potential, that is the harmonic oscillator potential is given to you, and the particle is initially in the ground state, and an infinite potential barrier is suddenly created at x is equal to 0. So, at x is equal to 0 there is a infinite potential. So, we can expect that at x less than 0 the potential will be, the wave function will be 0, and so the particle is confined to one side of the origin, and that is the probability of finding the particle in the ground state of the new potential. So, what is that probability? That so, what is the probability of finding the particle in the ground state of the new potential which was suddenly created? Then the normalized wave function of the harmonic oscillator potential are given to you. So, this is the normalized wave function. Then the alpha is nothing but square root of m omega upon h cross, and the Hermite polynomial is given to you, which we will require while we perform the integration. So, now let us get started with. Now, what is given to you is basically let us write by sudden approximation theorem. What we can say that the wave function for wave function of the particle do not change or does not change with this sudden creation of the infinite barrier potential. However, the wave function will remain the same, and the new wave function you can see it as, so let me call it as psi 1 prime, will be the new wave function, that is psi 1 will now become psi 1 of x divided by square root of 2. The factor 1 by root 2 is the normalization factor. So, now the wave function of the new or the new wave function is nothing but the old wave function which is normalized. So, the wave function remains the same, and let us see what happens to the probability of finding the particle in the ground state for this new wave function. So, the probability, and one more thing that we must note, that this wave function is true for x greater than 0, and our wave function is 0 for x less than 0, because the potential or the infinite potential is suddenly created at x is equal to 0. So, at x is equal to 0, an infinite potential is being created. So, for x less than 0, the wave function would go to 0, and so the probability of finding, so the probability of the finding the particle in the ground state with the new potential would be, so in general how do we write the probability? It would be probability would be given by psi 1 prime over psi naught the whole square. Okay. So, or rather the other way around we can write psi as psi 1 prime, okay, and the integration is from 0 to infinity. So, now we know what is psi naught and we know what is psi 1 prime. So, we are given the wave function which is normalized. So, now let me write first this psi 1 prime in terms of psi. So, this is psi upon root 2, okay, and we have 0 to infinity psi square. So, now when I rewrite the entire expression of psi naught and psi 1 from the given expression, what I obtain is 1 by root 2 times I have alpha by square root of pi. This is for this is for psi naught. So, when psi naught, so I have here this expression where I have psi naught will be alpha 2 raised to 0, that is 1. So, I will have alpha upon square root of pi raised to the square root of alpha into root pi e raised to minus alpha x square upon 2 h naught. Okay. And h1 psi 1 will be alpha upon 2 pi by n. So, now let us continue with this. We will have e raised to minus alpha square x square by 2. I will have a h naught alpha x, okay, and another expression will again have alpha. So, this power will go. So, I have multiplied by, so I have integral 0 to infinity. I will just write here alpha upon square root of pi the whole raised to half e raised to minus alpha square x square by 2, and I have a factor of 2 here, and this will be h1 alpha x. So, now in order to simplify this entire thing multiply by dx. Okay. I have dropped that in all the places. Now, we need to simplify this further. So, here we can see we will have e raised to x square alpha square x square, and this part of the integral will also get simplified, and you will be left with square root of, there is a whole square in this, right. This is whole square. So, when you take this out, you will have alpha square. So, I will just take the 4 pi term out, okay, this entire square. So, this is 2 and this is 2 pi. So, I will have a 4 pi and I will have e raised to minus alpha square x square. I have an alpha square term h naught and h1, okay, dx. Now, remember h naught of alpha x in this case will be 1 and h1 alpha x will be 2 alpha x. So, when I substitute this, I get 4 pi from 0 to infinity, and then I will have e raised to minus alpha square x square. Then I have from the previous, oh sorry, here it was an alpha only. One alpha will be picked from h1. So, here h naught is 1, h1 is 2 alpha x. So, I will have 2 alpha x dx, and I had 1 alpha before. Okay. So, this will be 4 pi 0 to infinity, and then this I can write as standard form. You can just substitute alpha square x square is equal to some t, and this will give me e raised to minus t dt, or just this is nothing but just 1. So, the probability is 1 by 4 pi. So, now this was the second, this was the fourth problem on Hermite polynomials, and now let us discuss a very simple problem to end this tutorial session, which I think it is very simple, but let us do it. It can be done in various methods, and I will be applying this way of doing this problem. So, what will be norm of psi plus phi the whole square? How will I write this? I can write this as psi plus phi, psi plus phi. Okay. I can write this norm as psi plus phi. Okay. I am writing the norm square of psi plus phi as this. Now, this associative property we use, this will be nothing but psi on psi, phi on phi, plus the cross terms, this plus. Okay. Now, from here you can see that this will always be greater than 0. We know from the norm of a vector is always 0, is greater than 0, sorry. So, now we have to worry about these two, are they equal. So, let us apply, let's use Cauchy-Schwarz inequality. So, from Cauchy-Schwarz inequality, what do we know? We know that psi on phi, that is any vector on the other, is given by, okay. So, this norm is always less than the norm of psi and norm of phi. So, using that we can rewrite this as psi, okay. I have a psi square, this is nothing but I can write it as phi square, that is I can write this as psi square plus phi square plus 2 psi times phi. When I am doing this, this will be less than or equal to this, because I am substituting for the psi on phi and phi on psi. So, this will be nothing but psi plus norm of phi the whole square, which would imply the expected result is always less than or equal to the individual vectors. Okay. So, now with this I think we can stop here, and we will have more tutorial problems based on so what's next would be coming up would be linear vector space, and more interesting problems based on linear vector space we will be discussing in the next class. They are more like math problems and you will enjoy doing them, and the lectures would give you an insight of the math part, the relevance of the math part with the quantum mechanics. So, see you later.